Wow. So this thin film problem actually comes courtesy of one of my CP students, Megan. Megan, if you're out there, you know who you are. Thank you for this problem. I asked her for some random numbers, and this is what she gave me. She gave me that some light, and it's going to be like a violetish color based on the wavelength of 467 nanometers. Some violet light is coming down through some medium. I don't know what it is, but it has an index of refraction of 3.7, and it's entering a thin film of thickness T, which we'll have to solve for, of 2.9 for the index. And then the backside of that film has an index of 1.5. What we would like to know is what is the minimum thickness? So what is the min thickness? What is the minimum thickness of T such that you will have a first bright maxima? So the first bright maxima comes into existence, okay? So pause this video for a second, take some time, and see if you can figure this out. Okay, so let's actually dive into how to solve this problem. As the light is going to be coming in straight down, and then it's going to be coming straight out with like a reflection here, but that's hard to draw, so let's draw it like this. The light comes in, bounces off the surface, comes out, okay? And then some of this light passes through, and then it comes out and keeps going. This first part up here, we're going to call this, this collision that happens here, this is possibly some shift. We'll call it delta A. And the question becomes, is this a hard shift or a soft shift, a hard or soft reflection? Because if it is a hard reflection, we're going to have a phase change of lambda over 2, 180 degrees. If it's soft, we're going to have a phase change of nothing. So what is it, hard or soft? Well, we're going from a high index to a low index. And if we're going from high to low, that's going to be a soft reflection. So this change of the A pathing is 0. Nothing's going on there, okay? For the light that travels through the transmitted light that reflects off the back here, this is some change in path delta B. And it will always be at least twice the thickness of the film, because the light has to go through the thickness of the film down and then the thickness of the film up. So it's always going to have some extra path length there. The question is, do we add a hard or a soft reflection to it? Well, in this case, we're going from 2.9 to 1.5. That is high to low. That's a soft reflection. So we don't add anything. So this delta B is just going to be 2 times the thickness of the film. So when we set up our total change of path length, it's going to be delta B minus delta A. That's going to be 2t minus 0. So we are just going to have 2t equals something. And if we're looking for maxima here, this will just be equal to m times lambda, because we know that when we're full integer wavelength differences, we're going to have a bright spot for this thin film interference. It's very similar to the double slit. So we ask ourselves the question, what is the smallest value of m we could have to get this to work for the first maximum? M cannot be 0 here, because if m is 0, then 0 times the wavelength is 0, and that means the thickness has to be 0, and that doesn't make sense. We have to have some thickness here in the problem. So m is going to be 1, which means that we will find our thickness by saying T is equal to lambda over 2. Or is it? So while we've done the math correctly, we're not fully done with this problem yet. The thing to remember is that this wavelength is in the film. It's in N2 right now. So what we really need to do is we need to say, look, this wavelength here, that wavelength in the film is equal to the wavelength proper, which is our 400 and what was it, like 67 or something like that? Yeah, the 467. So this was 467 nanometers divided by the index of N2, we need to take this and put it into this equation. So our true answer for our thickness is going to be the lambda proper, which is the 467 nanometers, divided by 2, because that's what we found here, multiplied by, or rather, divided by, or however you think about doing that math, N2, which in our problem was 2.9. So there needs to be a 2.9 that pops up in there. Okay, so that is our true complete answer, lambda over 2, and then don't forget about your wavelength being in the film itself. It's slowing down. We have a new lambda. That's how we solve that problem. Okay, so we're going to do another example of this, but for now, this one is finished. Bubblegum, bubblegum.